Chemical properties of S-block elements is that they exhibit fixed oxidation states. The oxidation state, also called the oxidation number, represents the apparent electrical charge an atom has after losing or gaining electrons during a chemical reaction. Since S-block elements are highly electropositive metals, they almost always lose electrons rather than gain them. The number of electrons they lose determines their oxidation state. Because group 1 elements always lose 1 electron and group 2 elements always lose 2 electrons, their oxidation states remain fixed at +1 and +2. Respectively, this predictable behavior is one of the defining characteristics of S-block elements and makes them easier to study than many transition metals, which can exhibit several different oxidation states. The image divides the S-block into 2 sections. The first section represents Group 1, also known as the Alkali Metals, while the second section represents Group 2, known as the Alkaline Earth Metals. Each group has its own characteristic oxidation state that remains almost constant in nearly all of its compounds. The image first explains the oxidation state of Group 1 alkali metals. These elements include lithium, sodium, potassium, rubidium, cesium, and francium. All of these elements have the same general electronic configuration, Nd. This means every group 1 atom possesses 1 valence electron in its outermost shell. Because only 1 electron is present in the outermost shell, very little energy is required to remove it. The nucleus does not hold this electron very strongly because it is relatively far from the nucleus and is shielded by the inner electron shells. Consequently, during chemical reactions, Group 1 metals lose this single valence electron very easily. For example, sodium undergoes the following process, Na plus E here. 1 sodium atom loses 1 electron and becomes a positively charged sodium ion. Similarly, Kk plus E shows potassium losing 1 electron to form a potassium ion. Every group 1 metal behaves in exactly the same manner. Since each atom loses 1 electron, every atom develops a single positive charge. For this reason, the oxidation state of group 1 elements is always +1. The image emphasizes this point by stating always oxidation state tuck +1. The reason this oxidation state remains fixed is that losing 1 electron allows these atoms to achieve the stable electronic configuration of the nearest noble gas. For example, sodium has the electronic configuration 28-1 after losing 1 electron. It becomes 2008. This is exactly the electronic configuration of neon, a noble gas with a completely filled outer shell. Likewise, potassium changes from 2008-1 to 2008, which is the electronic configuration of argon. Since this arrangement is extremely stable, the atoms naturally prefer to lose 1 electron rather than gain several electrons. The image also explains the oxidation state of Group 2 alkaline earth metals. These include beryllium, magnesium, calcium, strontium, barium, and radium. All Group 2 elements possess the general electronic configuration. This means every atom contains 2 valence electrons in its outermost shell. During chemical reactions, both of these electrons are removed. For example, Mg plus 2e shows magnesium losing 2 electrons to become a magnesium ion carrying a positive charge of +2. Similarly, Ca² plus 2e shows calcium losing 2 electrons to produce a calcium ion. Since 2 electrons are removed, every group 2 atom acquires a charge of +2. Therefore, the oxidation state of all group 2 elements is +2. The image again emphasizes this by stating always oxidation state toke +2. Like group 1 elements, group 2 metals lose their electrons because doing so allows them to attain a stable noble gas electronic configuration. For example, magnesium has the electronic configuration 282. After losing 2 electrons, it becomes 2. 8, which is the electronic configuration of neon. Calcium changes from 2 out 8, 8, 2, 2, 2 out 8, which is the electronic configuration of argon. Because noble gas configurations are extremely stable, group 2 metals naturally lose both of their valence electrons during chemical reactions. The image also provides an excellent flow diagram explaining how oxidation states are formed. It begins with valence electrons. Every atom possesses one or more electrons in its outermost shell. The next step is electron loss during a chemical reaction. S-block elements lose these outermost electrons. The next step is positive ion formation. After losing electrons, the atom becomes a positively charged ion because it now contains more protons than electrons. Finally, the charge on the positive ion becomes the atom's oxidation state thus. The oxidation state is simply the numerical value of the positive charge produced after electron loss. The image summarizes this relationship as group 1 plus 1, group 2 plus 2. This simple rule is one of the easiest trends to remember in chemistry. Another important point illustrated in the image is the relationship between valence electrons and oxidation state. For group 1, 1 electron lost plus 1 oxidation state. For group 2, 2 electrons lost plus 2 oxidation state. Thus, the oxidation state directly corresponds to the number of valence electrons removed. The image also compares the electron shells of group 1 and group 2 atoms. Group 1 atoms contain 1 outermost electron, whereas group 2 atoms contain 2 outermost electrons. This visual comparison helps explain why the oxidation states differ by exactly 1 unit. It is important to understand the difference between oxidation state and ionic charge. For S-block elements, these two quantities are usually the same. For example, Na has an ionic charge of +1, so its oxidation state is also +1. Mg has an ionic charge of +2, so its oxidation state is also +2. However, in more complex compounds involving transition metals, oxidation state and actual ionic charge may not always represent exactly the same physical situation. For S-block elements, however, they almost always coincide because these metals form simple ionic compounds. The fixed oxidation states of S-block elements explain many of their chemical properties. Because group 1 metals always form M-ions, they produce compounds such as Nocl Kb Urar Lif NaO in every compound. Sodium remains in the +1 oxidation state. Similarly, group 2 metals always form M-ions, producing compounds such as MgKo Baso, MgCaco. In all these compounds, magnesium and calcium remain in the +2 oxidation state. Unlike many transition metals, which can show several oxidation states, S-block elements almost never exhibit variable oxidation states. For example, iron can exist as Fe and Fe, while copper can exist as Q and Q. In contrast, sodium always forms Na, and magnesium always forms Ing. This fixed oxidation state greatly simplifies the chemistry of S-block elements. The fixed oxidation states are also responsible for the formation of predictable ionic compounds. Since the charges are always known, chemical formulas can easily be written. For example, sodium oxide. Now 2 sodium ions combine with 1 oxide ion to produce a neutral compound. Magnesium chloride. MgCl1 magnesium ion combines with 2 chloride ions to produce a neutral compound. The balancing of ionic charges directly depends on the oxidation states of the participating ions. The image concludes with an important statement. S-block elements exhibit fixed oxidation states because they lose all their valence electrons to achieve a stable noble gas configuration. This statement summarizes the entire concept. Atoms naturally seek maximum stability, since losing 1 electron or 2 electrons allows them to attain completely filled outer shells like the noble gases. They consistently exhibit fixed oxidation states during chemical reactions. The oxidation state of S-block elements is determined by the number of valence electrons they lose during chemical reactions. Group 1 alkali metals possess the general electronic configuration Ns, lose one valence electron, form M-ions, and therefore always exhibit an oxidation state of +1. Group 2 alkaline earth metals possess the general electronic configuration Ns, lose two valence electrons, form M-ions, and therefore always exhibit an oxidation state of +2. These fixed oxidation states arise because electron loss allows the atoms to achieve stable noble gas electronic configurations. As a result, S-block elements form predictable ionic compounds, display highly regular chemical behavior, and are among the easiest groups of elements to understand in the periodic table. Properties of S-block elements is their low ionization energy. Ionization energy is defined as the minimum amount of energy required to remove the outermost electron from an isolated gaseous atom. In simple words, it tells us how much energy is needed to pull the outermost electron away from an atom. If only a small amount of energy is required, the atom has low ionization energy. If a large amount of energy is required, the atom has high ionization energy. Since S-block elements have one or two loosely held valence electrons, they require only a small amount of energy to remove these electrons. This is why they have some of the lowest ionization energies in the entire periodic table. The image explains that S-block elements have low ionization energy because they possess one or two valence electrons. Group 1 elements have the general electronic configuration Ns, while Group 2 elements have the configuration S. These valence electrons are located in the outermost shell and are much farther from the nucleus than the inner electrons. Since only one or two electrons occupy the outer shell, the atoms can achieve a stable noble gas configuration simply by losing these electrons. Therefore, the atom naturally tends to lose them during chemical reactions. The image also points out that S-block elements have a large atomic size. As we move down Group 1 and Group 2, every new element gains an additional electron shell. Each extra shell increases the distance between the nucleus and the outermost electron. For example, lithium has only 2 electron shells, sodium has 3, potassium has 4, rubidium has 5, and cesium has 6. As the number of shells increases, the outermost electron moves farther and farther away from the nucleus. Because the attractive force between opposite charges decreases with increasing distance, the nucleus cannot hold the outermost electron as strongly. Another reason shown in the image is weak nuclear attraction. Although the nucleus contains positively charged protons that attract negatively charged electrons, the inner electron shells block or shield much of this attraction. This phenomenon is called the shielding effect. The inner electrons repel the outermost electron and reduce the effective nuclear charge experienced by it. As a result, the outermost electron feels only a weak attractive force from the nucleus. The image also explains that the outer electron is far from the nucleus. This greater distance further weakens the electrostatic attraction between the nucleus and the valence electron. Because the electron is only weakly held, it can be removed with relatively little energy. For these reasons, the outermost electron of an S-block element is easily removed. The image summarizes this idea by showing that a weakly held outer electron leads directly to low ionization energy. The center of the image illustrates the process of ionization. An atom is shown with its electron shells, and an arrow labeled ionization energy represents the energy supplied to remove the outermost electron. When sufficient energy is provided, the outermost electron leaves the atom, and the atom becomes a positively charged ion. The image also presents the electron removal process using several examples. For sodium, the process is Na plus E. This means a sodium atom loses one electron and becomes a sodium ion carrying a +1 charge. For potassium, Kk plus E. Potassium also loses one electron and forms a potassium ion. For magnesium, Mg+2e magnesium loses 2 valence electrons and forms a magnesium ion carrying a +2 charge. These equations demonstrate that ionization is simply the removal of electrons from an atom. It is important to understand that ionization energy is measured before the electron is removed. It represents the energy needed to start this process. Once enough energy is supplied, the electron separates from the atom, leaving behind a positive ion. The image also explains an important relationship. Weakly held outer electron low ionization energy easy, electron loss positive ion formation high reactivity. This sequence summarizes the behavior of s-block elements perfectly. Since the outermost electron is weakly attracted to the nucleus, only a small amount of energy is required to remove it. Easy electron removal produces positive ions very quickly. Because these atoms lose electrons so readily, they react vigorously with water, oxygen, chlorine, acids, and many other substances. Therefore, low ionization energy is one of the main reasons s-block elements are highly reactive. The image also presents the trend of ionization energy in Group 1 using the elements. Lina Karbs below these elements. The image shows an arrow labeled ionization energy decreases. This means that as we move down Group 1, the first ionization energy becomes progressively smaller. The reason is straightforward. Every element lower in the group has one additional electron shell. The increased distance between the nucleus and the valence electron, together with greater shielding from the inner electrons, weakens the nuclear attraction. Consequently, the outermost electron is removed more easily. The image also shows another arrow labeled reactivity increases. This illustrates the direct relationship between ionization energy and chemical reactivity. As ionization energy decreases, electrons become easier to remove. When electrons are removed more easily, metals react more readily. Therefore, reactivity increases down Group 1. For example, lithium has the highest ionization energy among the alkali metals and is therefore the least reactive. Sodium has a lower ionization energy than lithium, so it is more reactive. Potassium has an even lower ionization energy and reacts more vigorously. Rubidium and cesium have extremely low ionization energies, making them among the most reactive metals known. The same general trend also occurs in Group 2. Beryllium has the highest first ionization energy in Group 2, while barium has one of the lowest. As we move downward from beryllium to magnesium to calcium to strontium to barium, atomic size increases, nuclear attraction decreases, and ionization energy becomes smaller. Consequently, Group 2 metals also become increasingly reactive down the group. It is also useful to understand the meaning of the term first ionization energy. The first ionization energy refers specifically to the energy required to remove the first electron from a neutral atom. For example, Na plus E, the energy needed for this process, is called the first ionization energy of sodium. Similarly, Mg plus E represents the first ionization energy of magnesium. Since magnesium still contains another valence electron after the first electron has been removed, additional energy is required to remove the second electron. This is called the second ionization energy. For Group 2 elements, the second ionization energy is still relatively low because removing the second electron allows the atom to attain a stable noble gas configuration. However, removing a third electron would require an enormous amount of energy because that electron would come from a completely filled inner shell. Therefore, Group 2 elements normally lose only 2 electrons and exhibit a fixed oxidation state of +2. Low ionization energy also explains many other important properties of s-block elements. Because electrons are removed easily, these metals are excellent reducing agents. They donate electrons to other substances during chemical reactions. Because electron loss occurs readily, they form positive ions very easily. Because they readily lose electrons, they also form ionic compounds with non-metals such as chlorine, oxygen, sulfur, and nitrogen. Low ionization energy is also responsible for the vigorous reactions of alkali metals with water. When sodium is placed in water, it immediately loses its outermost electron, forming sodium ions and releasing hydrogen gas. The ease of electron removal initiates the entire chemical reaction. Similarly, reactions with oxygen, chlorine, and acids all begin with the loss of valence electrons. Thus, low ionization energy serves as the foundation for almost all chemical reactions of S-block elements. The image concludes by stating, S-block elements have low ionization energy because their outermost electron is weakly attracted to the nucleus and can be removed easily. This statement summarizes the entire concept perfectly. Ionization energy is the minimum energy required to remove the outermost electron from an isolated gaseous atom. S-block elements possess one or two loosely held valence electrons, large atomic sizes, strong shielding effects, and weak nuclear attraction for their outermost electrons. Consequently, only a small amount of energy is needed to remove these electrons, giving S-block elements low ionization energies. Easy electron removal leads to the formation of positive ions, strong metallic character, excellent reducing ability, and high chemical reactivity. As we move down Group 1 and Group 2, atomic size increases, ionization energy decreases, and reactivity increases because the outermost electrons become progressively easier to remove. Ionization energy is therefore one of the most fundamental concepts for understanding the physical and chemical behavior of the S-block elements.